Ask a truck driver what makes diesel different from gasoline, and you will get a confident answer. More torque. Better for heavy loads, lasts longer, built for big engines. And here's the thing. All of that is true, sort of, but it is also not the answer. It is describing the symptoms while completely missing the cause. When you miss the cause, you miss something that changes how you understand every truck you have ever passed on the highway, every ship that has ever crossed an ocean, and every piece of food in your refrigerator that did not grow in your backyard. The real difference between diesel and gasoline is not about torque, toughness, or engine size. It involves two completely different ways of making fire. One uses a spark. One uses pressure alone. That sounds like a technical footnote. It is not. The consequences of that difference, for efficiency, for global trade, for the cost of nearly everything you have ever bought, run a lot deeper than anything you have been told at a fuel pump. The history of how we ended up here involves a 19th century German engineer who intended this engine to run on peanut oil, and a plan for the world that went spectacularly sideways. By the end of this video, you will know exactly why compression ignition won. You will realize you have been surrounded by its output every single day without knowing what you were looking at. Let's start with what everyone gets wrong. Ask most people what makes a diesel engine different from a gasoline engine, and you'll get some version of the same confident answer. It's more powerful. It's for heavy vehicles. It's designed for big loads. All of that is partially accurate. None of it explains what's actually happening inside the engine. Here is the mechanical reality. Your car's gasoline engine mixes fuel and air, compresses that mixture, and then fires a spark plug to ignite it. The spark is doing the work of starting the fire. Every combustion cycle, hundreds of times per minute at highway speed, depends on an electrical spark to happen. Remove the spark, and the engine stops. A diesel engine has no spark plugs, not malfunctioning ones, not hidden ones, zero, not one. Instead, a diesel engine compresses only air, and it compresses it at ratios that would destroy a gasoline engine. A typical gasoline engine compresses its air-fuel mixture to roughly 8 to 12 times its original volume. A diesel engine compresses air alone to ratios of 14 to 25 times its original volume, more than double. When you compress air that aggressively, something happens that most people do not expect. The temperature of that compressed air rises dramatically to somewhere between 500 and 700 degrees Celsius, hot enough to ignite diesel fuel the moment it is injected. The fire starts from the heat of compression alone, with no spark required at any point. This is called compression ignition. One engine makes fire with a spark, one makes fire with pressure. That distinction sounds like an engineering footnote. It is not, because the difference between how you start the fire changes how much energy you extract from it. And that gap in energy extraction is where the real story begins. But that mechanical difference, no spark, pure pressure, is just the surface. What it actually changes is something that determines the economics of every freight operation on Earth. And the number is more surprising than you would expect. Here is what compression ignition actually does for you. It is not about raw power in the way people mean when they say diesel is more powerful. It is about efficiency, specifically how much of the energy stored in the fuel actually gets converted into motion versus wasted as heat. A modern gasoline engine converts somewhere between 25 and 35% of its fuel's energy into useful work. The rest escapes as heat through the exhaust, radiates off the engine block, or disappears into friction. Put $50 worth of gasoline into a car, and you are getting maybe $15 worth of actual forward motion. The rest is waste. A modern diesel engine converts 40 to 45% of its fuel's energy into useful work. That might sound like a modest improvement on paper. At the scale of commercial freight, it is the difference between an economically viable system and one that is not. Why the gap? It comes down to a principle called the Carnot efficiency limit, the theoretical maximum efficiency of any heat engine, which is determined by the temperature difference between the hot combustion gas inside the cylinder and the cooler exhaust gas leaving it. A larger temperature difference means more energy gets extracted as work rather than escaping as heat. Think of it like wringing water from a wet cloth. A light squeeze gets some water out. Wringing it tight gets most of it. Higher compression is the tighter squeeze. Diesel wins the efficiency contest because it compresses air more aggressively. And that higher compression is only possible because diesel fuel does not detonate unpredictably under pressure. Gasoline does. Try to compress a gasoline-air mixture to the ratios a diesel engine uses, and the fuel ignites before the piston reaches the top. Uncontrolled, destructive. What engineers call knock. So diesel's efficiency advantage is not a design preference. It is a consequence of the fuel's chemistry, which raises the obvious next question. What exactly is diesel fuel? How is it different from gasoline? Because the answer is genuinely backward from what most people assume, and it changes how you understand everything else about this engine. If you had to guess which fuel, gasoline or diesel, is more processed, more chemically refined, more altered from raw crude oil, you would almost certainly say diesel. The fuel for industrial machines, the heavy industrial product, must require more industrial processing. You would be wrong. Gasoline is the more refined fuel. Crude oil enters a refinery and goes through fractional distillation, careful heating that separates it into fractions at different temperature ranges. Gasoline comes off at lower temperatures. After that initial separation, it requires additional chemical steps, catalytic reforming, blending, additive packages, and precise formulation. It is the product of more industrial processes, more chemistry, more deliberate engineering. Diesel fuel comes off the distillation column at a higher temperature range. It is a heavier fraction, less processed, chemically closer to raw crude oil. If you held both fuels in a clear container, gasoline would be nearly transparent. Diesel would be slightly amber, noticeably oily. And yet, diesel contains roughly 9% more energy per gallon. The two fuels are also rated by completely different quality standards that measure opposite things. You have seen octane ratings on gasoline pumps, 87, 89, 91. Octane measures resistance to ignition under pressure. A high-octane fuel resists prematurely detonating when compressed, exactly what you need in an engine built around a controlled spark. Diesel is rated by cetane number. Cetane measures how readily the fuel ignites when exposed to heat and pressure. High cetane diesel catches fire eagerly. You want it to because the entire engine is built around the principle that the fuel ignites the instant pressure and temperature cross a threshold. Octane measures resistance to ignition. Cetane measures eagerness to ignite. The fuels are, by thermodynamic design, opposites of each other. Now here is the part that should stop you. The man who invented compression ignition, the engineer who worked out this entire system of fire by pressure in the 1890s, never intended his engine to run on petroleum diesel. His original engine ran on something completely different, and his vision for what this engine would do for the world was almost the opposite of what it became. Rudolph Diesel was a German engineer, born in Paris to German parents, who published his theoretical framework for the compression ignition engine in 1892. His first working prototype ran in 1897 at the MAN factory in Augsburg, Germany. The engine ran for 58 uninterrupted seconds on its first successful trial. The engineering community called it a revolution. At the 1900 Paris World Exhibition, Diesel demonstrated his engine running on peanut oil. Not petroleum diesel, peanut oil. Diesel's stated purpose had never been to build a better truck engine. It was economic and social. He believed that small manufacturers, farmers, and craftsmen were being crushed by the industrial scale of coal-powered factories. Steam engines required massive infrastructure and coal shipped from mines owned by large industrial corporations. Diesel wanted to build an engine that could run on locally available fuels, vegetable oils, plant-based fuels, whatever a small operator could grow or produce themselves. His theoretical writings described explicitly a future in which agricultural communities generated their own fuel from crops and operated independently of both the coal industry and the petroleum industry. In the language of today, he was describing distributed energy production and fuel independence. He was also describing what we now call biodiesel, because diesel engines can run on vegetable oil. They always could. The fundamental chemistry of compression ignition works with any energy-dense oil that auto-ignites under heat and pressure. The petroleum diesel we use today was not Rudolph Diesel's intended fuel. It was the fuel the petroleum industry supplied when petroleum became cheap and abundant, and it happened to work. Diesel disappeared from the steamship Dresden, crossing the English Channel on the night of September 29, 1913. His body was recovered from the North Sea about 10 days later. He was 55 years old, financially ruined despite his engine's commercial success, and in poor health. The reasons for his death are still debated. The engine he left behind went on to do almost exactly the opposite of what he had intended. It became the backbone of the petroleum economy, the engine that made global container shipping, long-haul freight, and diesel-electric railways possible, all running on petroleum fuel refined from the same industrial supply chains Diesel had hoped to circumvent. His name is on the fuel, on the engine, on every truck stop in America. Most people have never heard it. Here is the number that should make you pause. Approximately 95% of all Class 8 freight trucks in the United States run on diesel. Not most of them. Essentially all of them. But trucks are only the most visible part of the picture. Every major ocean-going container ship runs on a diesel engine. The Wärtsilä Sulzer 14RT Flex 96C, installed in the Emma Maersk when she launched in 2006, produced over 80,000 horsepower and weighed approximately 2,300 metric tons. And at the time, it was the most powerful diesel engine ever built. It ran on the same compression ignition principle Rudolph Diesel worked out in 1892, scaled to a size he could not have imagined. American freight trains run on diesel-electric power. A massive diesel engine generates electricity, which drives electric motors at the wheels. A single freight locomotive produces 4,000 to 6,000 horsepower from compression ignition. One locomotive, one engine. The same fire by pressure. Add construction equipment, agricultural combines, hospital backup generators, port cranes, irrigation pumps, refrigerated warehouses. The industrial infrastructure of the modern world runs on compression ignition engines, on Rudolph Diesel's thermodynamic principle. That banana in your kitchen in January traveled in a refrigerated container on a diesel ship, was offloaded with a diesel crane, moved to a distribution center in a diesel truck, and delivered to your grocery store in another diesel truck. The same engine, every step of the journey. The United States burns approximately 47 to 50 billion gallons of diesel per year across trucks, trains, ships, and construction equipment. Not because anyone mandated it, because compression ignition's efficiency advantage made it the financially dominant choice at every scale above a passenger car. Rudolph Diesel wanted his engine to free small farmers from industrial monopolies. Instead, it became the engine the industrial economy cannot run without. And here is what all of that means for you specifically, and for everything that has ever reached your doorstep. You came in with the truck driver's answer: more torque, lasts longer. Built for heavy loads. That answer is not wrong, but now you know why it's true, and why it matters more than what. Compression ignition. Pressure made fire. Air compressed so hard it reaches 700 degrees on its own, and diesel fuel that ignites the instant it touches that heat. Higher compression ratios extract more energy from the same fuel, 40 to 45%, versus the 25 to 35% a gasoline engine manages. That gap is not a design preference. It is a thermodynamic consequence baked into the physics of how you start the fire. The fuel itself is less refined than gasoline, heavier, closer to raw crude, and yet carries more energy per gallon. The two fuels measure opposite qualities. Gasoline rates its resistance to ignition. Diesel rates its eagerness. Thermodynamic opposites, designed for thermodynamically opposite engines. The man who designed this system wanted to run it on peanut oil and hand it to farmers. His engine ended up running almost everything that has ever moved freight on the surface of this planet. Next time you see a diesel truck pulling away from a stop with that characteristic low RPM surge, you are not looking at a vehicle that got lucky with a powerful fuel. You are looking at compression ignition, Rudolph Diesel's pressure-made fire, doing exactly what the physics promises. And if you think the diesel engine is fascinating, wait until we get into the turbocharger. The device sitting on top of nearly every modern diesel engine uses nothing but the engine's own exhaust waste, energy that would otherwise disappear into the atmosphere to force more air in and make the engine more powerful. It is one of the most elegant pieces of engineering in any vehicle, and almost nobody thinks about it at all.